In this demonstration video, we are going to model a real data set. Let me first of all try and find it. It's called, the triangle group is called CTP. I'm going to open it. And you'll see that for this particular triangle group, we also have a vector called base exposure. This is real data, and the exposures we're using here, they represent the estimates of ultimate number of claims incurred for each accident year. And this data is real, it's published data, and basically these exposures were already calculated by, I think it was Greg Taylor in his paper. So the corresponding data set is the triangle, and we're going to use the base exposure. That means that for each accident year's paid losses will be divided by the corresponding exposure, and we call that the normalized data. So to start the modeling process, we go to the tabs Models, and the paid losses incremental, which is actually that data set is already highlighted. We go to the PTF modeling framework, where in this particular modeling framework we try and design a model which captures the trend structure in the three directions and also the volatility around the trend structure. Now, I'm going to be modeling these data manually in a pretty slow way. There are faster ways of doing it manually, and then also we're going to use the modeling wizard. And the reason I'm going to do it manually in a slow way is so that you get to learn some very basic statistical concepts. So our starting model has one parameter in each direction, and so along the development years we've estimated one trend, along the accident years one level, and along the calendar years one trend. If we look at a graph of the actual data, go to Plots, tab Data Plots, Log Normalized. We're looking at the logarithms of the normalized data. What have we done in essence is along the development years, this is the data log scale along the development periods, we've measured one trend. That is one line that has an intercept and a slope, and you can see that the slope of this line would be negative. If we look at the accident years, what we've done along the accident years is measured the average level, which sort of represents the average of all these observations. So it's the best flat line which is closest as possible to all these points. And along the calendar years, we've measured the average trend, which you can see might be slightly negative, approximately 0. So if we now go and check the model display, this is what we have estimated as a starting model. This is a starting model, very important. One trend along the development years, so this line has an intercept which is represented by the alpha on the right side, and a slope. That's the average level of all the values, and that's the average calendar year trend, which is approximately 0. So let's close that. And what we're going to do is first of all model the development year direction. And I'm going to be guided by you, but I guess you can't speak back to me, so I'm going to be asking you questions, and I'm pretty sure that you're going to know the answers. So along the development years, we've only got one trend parameter, and the question is the trend from 0 to 1 the same as the trend from 1 to 2? Now, most people might say it is the same, and therefore we will not add another parameter. Now, is the trend from 2 to 3 the same as the trend from 0 to 2? And I think most people would argue that it is a new trend, so I'm adding another parameter. Is the trend from 3 to 4 the same as 2 to 3? Now, most people diagnostically, when they view this, would argue that it is the same trend. Now, we're going to make a mistake and add another parameter, and then we'll show that the statistics of the model will tell you that you were right. Diagnostically, you do not need another parameter. So I'm adding another one, but the statistics will tell me that I don't need it. And then from 4 to 8, these lines are going to change around more because there are a few points. I will just add one parameter. Let's estimate that. And then you can see 0 to 1 and 1 to 2, most of the residuals in development year 1 are positive, so we do need another parameter. So let's estimate that. Let's tile vertically. And now if you look at the regression table, we're looking at the gammas. You'll notice that the line 3 to 4 is pink. The other thing you'll notice that this observation is relatively large. If we look at our diagnostic tools and look at the normality display, we can see that this observation is there. It's also there. In order to assign it 0 weight, you just click on it. It becomes black. It also becomes black on the residual display. So now we'll estimate the same parameters, but we don't use that observation. You'll notice that the line 3 to 4 is pink. That's telling us that we don't need that additional parameter that we knew originally diagnostically, but I added it to show you that the statistics will tell you that. So if we now look at the model display versus development years, you can see that the trend from 2 to 3 is minus 4.08. From 3 to 4, it is minus 4.093. So not only are they statistically the same, they're numerically the same. Now, in order for me to move that parameter manually, I would just click between 3 and 4 to get rid of the gray band, to get rid of that parameter. Another way of doing it is you just click on the Optimize button once. It removes that parameter and estimates the new model. So if we now look at the model display, you can see that you only have one parameter from 2 to 4. You don't have an additional parameter from 3 to 4. Now you'll see that this line here, 1 to 2, is sort of brown, burgundy. It's the same in the regression table. In order for me to set it to 0, I can click on the little box above the number 2 on the x-axis, and to set that parameter to 0, that's why the red line. I can also do it automatically by just clicking on the O. So the trend structure that we've identified along the development years is 0 to 1, 1 to 2 it's flat, it goes down, and then the decay is pretty strong. From 4 to 8, it's minus 65.82%, plus minus 4.29%, and later on we'll test to see whether that is stable. Let's look at the accident year direction. Now if we look at the accident years, most people would argue that, yeah, these residuals look pretty random. Some people won't be sure, and they would actually argue that these 2 years, 73 and 74, they do have quite a number of observations. So there's a new level, a lower level. Along the accident years, we have level parameters. They're like intercepts or heights. So let's introduce a new parameter from 72 to 73, 74 to 75. So we'll have one level up to 72, lower level 73 to 74, high level. Let's estimate that. Let's look at the model display, and this is what we've estimated. A relatively high level, 69 to 72, then it drops, then it increases. The differencing levels represent the trends, and so on. Okay, if you look at the regression table now, which very often, in fact, when we do things automatically, there's no need to look at the regression table because the model display has more information than the regression table and also displays the parameters graphically, so that much easier on the eye, much more descriptive. Now there's a pink line there and there's a blue line there. When we clicked on the O button, it just removed one parameter. If we click on the double O, it removes the first most insignificant change, then it goes to the next one if that's still insignificant, and so on. So it does it by backward elimination. So let's do that, and we find that there are no accident year changes. Let's go to the calendar years, and if we look at the calendar years, and if we just focus on the calendar years 75 to 79, and I asked you the question whether you believe that 75 to 79 are the trends stable or unstable. Now, I'd like to think that most of you would agree that the trend from 75 to 79 is stable. So that's already a story about the data. It kind of means that as I move my car backwards and I remove these years, I would expect the same distributions of reserves beyond 79. All right, the most unusual year here is 1974. It's quite interesting. The company paid much less in the calendar year 74. In 73, it paid the same level as 75, and thereafter it never made up for the low payments. One way of modeling this data is from 72 to 74 to have a new parameter. It goes down, relatively down, 74 to 75 up, and then 75 onwards, a flatter parameter. So down here, up there, and flatter there. Okay, let's estimate that. Let's change the regression table to the IOTAs. Let's look at the model display. And now you can see that it goes up, down, up, and relatively flat. If you now optimize, this is what you get. Okay, so basically the first trend is 0, the last trend is 0, you've got a drop, and then an increase. And let's save this model as, say, good. Now, how do we know that it's a good model? I mean, how did we design this model? We sort of used our eye, we examined the residual displays, decided whether we need more parameters or not, and then added them, and then we also used the O or double R button to get rid of any unwanted parameters. Okay, so if we look at the logbook, which keeps track of the various models we've estimated, some summary statistics, you'll see that the BIC is the lowest for a model that we've saved as good. It's 28.5. These are relative statistics. Their absolute values are not that relevant. 28.5. So this statistics is the best so far. The AIC is also the best so far. These statistics are discriminatory statistics. Between any two competing models, the one with the lower values is better. The statistics have got two components. One is how close are the fitted values to be observed, and also you get penalties for the number of parameters you use. So basically, these statistics guard you from adding any unwanted parameters. In other words, you're going to stick to the principle of parsimony, which is very important. You're going to separate the trend structure from the process variability with as few parameters as possible. Okay, so what is the model that we've identified? Let's see. It's got that development year trend structure. Excellent years are same level, no trends, except for some trends along the calendar years, which will project along the excellent years and the development years. So in a three-dimensional version, this is going to look like this. And you will see the valley in the 74 calendar year. An integral part of the model is the process variability. That's the variance of a normal distribution. Do we have normal distributions? The answer is in the affirmative. So let's look at the variances again. And it's 0.0621. Let's look at the standard deviation. It's 0.2493, so about 0.25. That means the coefficient of variation of the log normal on a dollar scale is at least 25% just based on process variability. So if a particular cell in the forecast table, the mean is, say, 10,000, then the corresponding standard deviation that cell will be at least $2,500. Now, if we're going to do a projection now, what assumptions are we making? We're making an assumption about this development pattern for each accident year. We're assuming that accident year is homogeneous, but we're also assuming that these two calendar year trends will project along the development years and the accident years. We're also assuming that normal distributions will have these variants. So we're going to forecast a future with a zero trend, and these forecast table get. So you can see that if you take any red value and divide by the corresponding black value, then you'll have a ratio which is at least 25%. If we go back to our model, the residuals, and now we're going to do the validation. That's the removal of years. Now, when we studied the triangle group M3IR5, that remember that had 3 inflation rates, it's one that we simulated. We removed 1 year, we might have removed 2 years manually. We also have what's called an auto validation module, where we're going to remove up to the last 4 years, 1 year first, 2 years, and 3 years, and 4 years. And we'll have one table depicting all the various results. So let's do that. So now if we scroll to the right, we will see how the mean reserve and standard deviation of reserves change. These are the mean of the reserve distribution beyond 79 and the standard deviation of the reserve distribution beyond the calendar year 79 as you remove data. And you can see that the answers are pretty much the same. It's pretty stable. This is a graphical depiction of that particular part of the table. So if you're sitting with your motor car at the end of 79, the mean reserve is 12.983 million. The standard deviation of the reserve distribution is just over 1 million. If you're sitting with your motor car at the end of 75 without having any of the data of 76, 77, 78, and 79, the mean of the reserve distribution is 13.382 and the standard deviation of 1.385. Very much the same. If we go back to the logbook, we actually see the way the trend since development year 4 changes as you move years. Let's go back to the model display. We have a trend of minus 68% plus minus 0.38 or 3.8% from 4 to 8. How does that parameter change as you remove years? Well, if you remove 4 years, it becomes minus 67.23 plus minus 12.4. How well would we have predicted the last 4 years ago? Well, this is a graph of the prediction errors, and it looks pretty good. Now, part of our prediction, in fact, an integral part, a very important part of our prediction, is that, let me find some space. Let me bring up the pointer. When we remove all these years, nothing there. For each cell that we've left out, we predict 2 quantities, the mean and the variance of the normal distribution. We're predicting normal distributions on a log scale for each cell. The normal distributions have got 2 parameters, the mean and the variance. We now test to see whether it's true that the 34 observations that whose distributions we are predicting, do they actually come from the predicted normal distributions? And the answer is in the affirmative. So let's see what we found out for this particular data. The projections of the means and standard deviations of the reserve distributions as we move up to the last 4 years remain pretty stable. And 4 years ago, we would have done a very good job in predicting the distributions of the 34 observations we left out, and we're only using 28 observations. Well, now, why is that happening for this data? What is it in the data that gives us this particular phenomena? Okay, stability. Stability of what? There's a stability of this calendar year trend, 0. 0 is pretty stable because as you remove years, it's still 0. And then you've got a stability of that trend. So in fact, it is true that there's a 0 trend there. And the data are pretty close to that 0 trend because the process variability is really not all that bad. And that trend is stable also. Next year, or next evaluation period, there's no need to design a new model. You can update the triangle group automatically, either using COM or kind of manually highlight it, update it. I'll show you how to do that. And you just do what's called forecast tracking and monitoring. Now, let's design a model in a different way. Let's go to the starting model again. And now I'll use what's called a wizard, that it builds the model. Okay. So I'll use the wizard first of all, one command at a time. Can you see it's adding parameters? and I'll just let it rip. And it's come up with the same model. The same model that we did manually, and that would have only taken a fraction of a second. Okay, now with our clients, we communicate in terms of models. And you know that when you run a model, you can save a model. Let's, for instance, close the PTF module. I can run the model. Let's go back to the triangle group. I can run the good model from here, from my actual triangle group. It's stored in the database. So once a model is saved, when it's run, you've got the model display, you've got all the other attendant displays. You can do the forecasting, forecast summaries. Later on we'll show you how you find distributions of reserves and so on. You can get all the attendant displays in a matter of seconds. Now, what did we actually find in the data? We found out that the accident years were homogeneous except for calendar year change. So it's very likely that condition 1 that we studied with when we looked at the extended link ratio of family, we came up with condition 1, and that is if you look at the incremental data in a particular development year, as you look at the data going down the accident year, it's just random, there's no trend. So if condition 1 is satisfied, it's very likely that ratios, or it is a fact that ratios don't have any predictive power. So if I now go apply extended link ratio of family to the paid losses cumulative, if I look at the residuals, one of the things you'll notice is that there is a bit of a downward trend in the residuals versus fitted values. We've just estimated the volume-weighted average, or if you like, the chain ladder ratios, but using regression. You also see we're underfitting a lot of these calendar years. So I guess if we do a forecasting, which is pretty meaningless, it's a little bit less than what we get. It's about $1 million less than what we get on the other side in PTF. If you look at the y-axis graphs, you'll see that you need an intercept, but the incrementals versus cumulatives are not correlated. So if I go to model templates, trend and ratio, and optimize twice, the best model in the extended link ratio of family basically sets all the ratios to 1, or ratio -1 to 0. There is a trend in development year 1. Let's check that. There is, I guess, there's a negative trend, but yet the incrementals versus the cumulatives are not correlated. Now, this is the best model in the ELRF. It conveys very little information. We still don't know what's going on in the numbers. We don't know the volatility. We don't know whether there's stability, and so on. And when we do our forecasting, we don't even know what we're assuming for the future. On the other side, PTF is still open. I think this model, we have an explicit description of it, and we know what assumptions we're making in forecasting, the distributions in every cell, and so on. Thank you.